Hi everyone. So I'm Zakir. I'll be today's chair for today's last large system working group session. Welcome to the large systems working group stream and to the third and last session for today. So for today's session, we have Rob Scott, a principal architect for mainframe system tools at Rocket Software. And if there's any questions throughout, please place them in the chat and I can then ask Rob throughout the presentation your questions. And if you'd like to unmute, there's the chance to unmute at the end, and then you can ask him directly yourself. And then the last thing, please, if possible, provide feedback, and you can do that by just going to the Build Your Own Agenda, clicking on the session, and there should be a link. That way we can improve our sessions for you. So now I'll pass it off to Rob to take us through advanced memory browse using SDSF. So Rob, the stage is yours.
Thank you very much. Yeah, and just to re-emphasize, I really encourage you guys, if you've got questions, please stick them in the chat. I'm very happy to pause where we are in the presentation and discuss whatever points you raise. This isn't a particularly long presentation. I don't think it's going to be more than about 40 minutes. So there's loads of time, loads of wiggle room to talk about stuff if it crops up. Okay, so I've been working on SDSF now, development for about 8 years. Rocket took over SDSF back in late 2015. So I've been with Rocket for about 20 years in total. Before that, I was a systems programmer, MBS systems programmer for 15 years or so. And during my time as a sysprog, I used to love sniffing around inside memory, inside dumps, inside any tools, online tools I can, having a look at control blocks, having a look at things. It just piqued my interest. So when we took over development of SDSF, one of the things we wanted to do eventually was to add a memory browse function inside of SDSF so that we could provide that sort of systems programmer satisfaction of curiosity about system memory and address-based memory. So we were able to introduce this in ZOS 2.5, and we have displays for both traditional like 24, 31-bit storage, and also we support 64-bit as well. We've got a variety of panels that you can launch a memory browse from, including various sort of address space level displays. And we've also got links in from system level displays as well. And this can go from things like, common storage usage, loaded modules, all that sort of stuff. So we now have this capability of driving this memory browse from those hyperlinks. But you can also type explicit primary commands on the SDSF command line to go and browse explicit addresses in your preferred address space from the command line. In ZOS 3.1, we were able to expand on this memory functionality. We've improved drastically the ability for SDSF to show memory in sort of a structure format, DSEC format. We've added in a IPCS-like run chain functionality inside the product, so you can process linked lists and things like that. And we've also added the concept of a user-defined structure maps as well. And we'll get into that a little bit later. And this is probably the most sort of selfish aspect of SDSF I've ever been involved in, because obviously as developers of system software, we are forever having a look at memory in various address spaces and system memory as well to satisfy debugging or just curiosity as we're looking for stuff. So this really is a labor of love, I think, as far as SDSF is concerned. Okay, so topics we're going to cover: browsing memory basics. So this is basically how you would use the native memory browse command inside of SDSF, how you would map structures, run linked lists, and allied other panels that enable you to do this. We have an address space diagnostics panel that you can use to launch your exploration of memory on ZOS. We'll then go through what we've got for common storage, various types of panels, including like authored common storage and summary displays by subpool and key, and also private storage analysis in the same sort of way. So we can look at private storage usage for a single address space and also summarize that by key and subpool as well. And a little bit of 64-bit at the end, just to show that we can have a look at that sort of memory as well. Okay, so basic browsing memory. So an unsurprising command called mem to enable SDSF to browse memory. Syntax is very simple, mem and then an address expression. We have got some little things that you can do inside that address expression to rather than just type out hexadecimal digits. An optional specification of the hexadecimal ASID, and if you're feeling particularly brave, you can also specify a system name if this address space is not on your local system. Now, we don't expect you to ever actually type that, but the functionality is there in case you wanted to use it in something like Rex or a batch job, and actually under the covers, there are places within the product where we are basically emulating that. If you do a point and shoot on a table that's come from a remote system and you're looking at memory, so the functionality is there. So we've got it in the syntax. So the default's 0 for the address. So if you just type in mem all by itself, you're going to be looking at virtual storage address 0, and you will be looking at your own user address space. ASID will default to your own user address space, and obviously your system name, if not specified, will default to your local home system. You can omit leading zeros from any hexadecimal keyword in the expression, and you can use an underscore to separate high and low half of an address if you're dealing with 64-bit addresses. Some examples here. So mem and then some 7F Charlie E8 will just show the memory at that hexadecimal address there in your own address space on the local system. Likewise, underneath, we're going into 64-bit land here with a mem 50 underscore, and then some hexadecimal characters, and then CD. So that's a 64-bit address where we're taking the high half before the underscore, and then the low half as the hexadecimal characters afterwards in address space 00 Charlie Dog. So that will enable a 64-bit memory browse in that address space. And then, this heroic syntax at the end here when we've actually specified the system name as well. But obviously, no real human is going to be typing that, but it is available within functionality. So we're very, very lazy typists in SDSF HQ, and a lot of our developers at Rocket are as well. So we don't really want to be typing out that mem command everywhere. So we have point and shoot capability within the product, and we have numerous panels now across the whole panel landscape in SDSF that have point and shoot enabled fields that invoke a memory browse service under the covers. I've tried to make this by default stand out a little bit more from the other sort of point and shoot fields, so that we have a default screen attribute is green and underlined, and it sort of matches some of the tools that I used to use as a systems programmer, in tools that I actually wrote back in the old days. I quite like that. But if you don't like it, you can change it from the set screen options dialog, and you can go into there, and there's options there to change the color, to change the attributes, and you can even sort of say, well, I don't want to use SDSF's point and shoot enabling functionality. I want to use ISPF's CUA way of indicating something is point and shoot instead. So you can select the CUA attribute option. Any ASID and system values when you do a point and shoot. So you imagine you have a row on an SDSF panel and there's an address on it, and you hit enter. Behind the scenes, there's obviously some sort of binary format record that represents that row, and it could well be carrying inside of it. You might be able to see it on the panel, you might not. but there'll be an ASID and a sysname value somewhere within that binary record. So if you do a point and shoot on a row on a table, we know what the ASID and system name is, and we will inherit that from the row and invoke the service to the correct place. Generally, common storage is considered owned by, if you're browsing common storage and you've specified an ASID on the mem command, it is considered owned by that ASID for the purposes of security. Or it is inherited from, as we said before, the ASID and the sysname on the row. And it is defaulted to the current ASID when otherwise unspecified. So if I went straight, if I just typed a mem command and some address ended up in common storage, that would just inherit the ownership of my ASID. So this is what it looks like if you do a mem command here. I do believe this is looking at the, looks like the CVT. So you have on the title line, you've got your local system and your system pattern. You then have the ASID and the job name of the storage that you are looking at. On the left-hand side of the screen is sort of like the fixed field, and that will contain, and it always contains a 64-bit representation of the address that you're looking at. It's followed then by a 4-character hexadecimal offset within that memory, and then we split the contents up in a sequence of words of 8-byte, that's sorry, 4-byte words, and we show the hexadecimal content of those words. Next to it is the EBCDIC representation of that data, and what you can't see on this panel is over to the right-hand side is also a column that shows the ASCII representation as well, and a few other attributes, and we'll come on to that a little bit later. Against the row in the NP column, you've got various actions that you can type. And the most common one probably is D, where you will show the memory at the nth word of the contents panel. Okay, so basically you can type in D and then a number. If you omit the number, you get 1. And that will say, right, okay, take the hexadecimal content from the nth word, 1, or the second word is 2, and treat that as a target 31-bit address. And behind the scenes, invoke mem with that 31-bit address. Likewise, we have a G, that accepts numbers from 1 to 3, because if you think about it, we've only got the maximum of 3 64-bit addresses that we can show in the contents. So it will take the nth word and the n+1th word, combine it together, build a 64-bit address. Behind the scenes, we've got the memory browse of that. Other interesting line commands you can do is the M, which will take this memory that you're seeing here in raw EBCDIC format and map that memory against a known structure. And we'll come on to that also a little bit later. And the final thing you can do is type an S, which is basically going to take the memory in the fixed field in the address column and take you to a memory browse session based on that address, so you can navigate through your list of memory that way. Off to the right-hand side are some more columns. So you can see here I've actually got a show columns dialog going on inside the product. And you can see here we've got EBCDIC. Underneath that, we've got the storage key, whether or not it's fetch protected, the ASCII representation, and then the job name, the ASID, the sysname, and the system level. So all that information is available as columns on the data row. Just to show you there is a lot more data to the right-hand side.
Rob, there's a question for you.
Yeah, sure.
The question is SDSF memory browse functionality protected by any security class, similarly to how browse of active storage via IPCS is protected?
Yes, it is. And we're going to come on to that in a couple of slides' time. Good question. And I'm glad that you're concerned about that, because we did think about that quite a bit. Funny enough, it's the very next slide. Okay, so obviously you don't want to allow any ninny on your ZOS system to browse storage from any address space. It could contain sensitive data. It could allow them to look at stuff that they shouldn't be able to look at. Now, the story is, under the covers, how are we doing this? We're not actually writing or sending any SRBs or anything out from the product itself. I had a chat to the guys over in Poughkeepsie, and we agreed that SDSF would use the same service that IPCS uses. So IPCS Active, if you've ever used IPCS Active to browse storage, that's got a service that it calls. So SDSF actually uses exactly the same service in order to achieve its goals. Now, the security provided by that service is pretty much a binary switch. You either have the ability to browse storage in another address space or not. Okay, we in SDSF HQ wanted a little bit more granularity than that. So in order to use SDSF's ability to browse storage, we've introduced a layer above that. So we have a SDSF class profile, ISF job dot storage dot whatever the owner of the address space is, whatever the job name is, and whatever systems are. Okay? And you need read access to that SDSF class profile in order to browse the memory. There are cases where we cannot derive the owner. You've got some system address spaces that aren't started after JES comes up, and they haven't requested job ID, and they haven't otherwise got some sort of representation of who their owner is. And if we can't work out what the user ID owner should be for that address space, we use 8+ signs. So you can cater for that inside the class profile if you want to protect those. Now, we did actually implement a little bit of extra functionality on top of the standard IPCS browsing capability, because what we noticed was if a page has never been referenced, the IPCS service comes back with a return code to sort of say, yeah, storage has been skipped because it's never been properly backed. It's valid, but nothing's there. And that led to some, in my view, some usability problems. I would have much rather have seen half a page of binary zeros, because it sort of matches my expectations of me dealing with a table of memory. So if you're like me and you agree with that, you can have an option to allow SDSF to just gently touch that page in order perhaps to bring back binary zeros for you instead. So if you've got control access to the same SAF profile as before, what we will do, we will send a tiny little SRB that just touches the first byte of that page, hopefully bringing in unreferenced storage, backing it so that we've got some binary zeros, which makes some of the displays a little bit more consistent. If you don't want that to happen, just keep the users with read access and you'll all be good. But you will see maybe some storage skip style messages or warnings that come up in the top right-hand corner. Okay, so with 3.1, we've added some enhancements. So the first one, big enhancement, is run chain. As a software engineer, we deal in linked lists all the time. As a systems programmer, you deal with linked lists all the time. And we thought it'd be really cool if you could run linked lists interactively from an SDSF memory session, memory screen. So we've added a run chain capability, and I'll show you what that looks like in a little bit. With 2.5, we did have the ability to show SDSF memory in a structure format, but we sort of run out of runway near to the release date, and we had to sort of put it into an SDSF browse section. So if you ever did this on 2.5, you were taken into a screen that looked very similar to a sysout browse, where we sort of produced a report of what it might look like in the structure. And we also provide a command called memcsr that you could assign to a PF key, which might make it work, picking up the address on the screen and invoking them under the covers. It wasn't great, but it was all right. The fact that we now use a traditional SDSF table display means that we can make the output a lot better. We can now have actions against the structure rows as well to support things like the D and G actions you've seen on the raw memory browse. We can support those on structures as well. Another limitation in 2.5 was all the structures were internal. So we had we ran some processes back at Rocket that produced the internal structure we needed to show the memory in structured format. And in 3.1, we decided to externalize. So we now ship all the control block maps that we use in a special member in ISET PRM statements. And then you can also add your own as well. So if you've got an ISV or a personal control block you'd like to model for the mem command, you can do that. And there are some harmless statements you can use in ISET PRM that'll enable you to do that. And I do show an example of what it looks like. And if anyone really is really interested in following it up, please let me know. I'll guide you through it. Slides on that, but it's not too bad. We did originally in history try and use the IPCS CBF service as well. We thought, well, why should we go to the trouble of modeling all these structures when Poughkeepsie have already done it? And we did try to do that, but it just didn't work with the way that we were trying to operate. So we had to go back and use our own internal skip. And I think this is probably how we're going to go from now on. We'll keep on using the maps. So if you wanted to browse your memory in some sort of structure format, let's go through it at the moment. So I'm looking at some storage here. It looks very similar to somewhere in the SSCT. Look over on the right hand side here, it looks very similar to an SSCT. And the user here has typed in M beside the row. And what SDSF is going to do at that point, he's going to sniff up to the first 16 bytes of that memory to see if he recognizes any character strings in those 16 bytes. And if he recognizes it, he's going to present you a pre-populated name field in a pop-up panel to sort of say, I reckon that what you're trying to map is an SSCT or CVT or your ACEE or whatever. Do you agree? And if you say agree, you press enter and off you go. Or you can blank it out, choose a sequence from this. We've got a whole slew of control blocks that you might want to map it instead. But you always get this prompt panel to sort of say, right, okay, are you sure this is what you want? And please press enter and I'll show you the results. Okay, so you've got this nice pop-up panel, you hit enter. And then you now see the structure displayed in a traditional SDSF table. So what we've got here is the field name on the left-hand side. And what we've also done behind the scenes is if we can recognize you've got something like a flag byte and there are equates for the various settings inside that flag byte, we will show those as well. And we will low light them. So you'll see here they've got a little plus sign. And we're showing you what the equated values are for that flag byte. And you can show it both in hexadecimal and in binary. So it's very easy if you're looking at a structure to see which bits are on inside of various flag bytes. You can also use the D and G actions against a row that contains an address. So for a 31-bit address, you can use a D. If it's a 64-bit address, you can use a G. And you can also use the M action against an address as well to show that address in the same map that you're currently on. So this allows you to process your linked list structure. You can go through your linked list in structure formats by just pressing M against your next. Show that. So the first example here, this is an imported slide from my 3.1 presentation I gave this morning. This is the display memory for a field within a map structure. So apologies for the white screen. This is in the theme of one earlier today. I I do have some people at Rocket who operate with this sort of color scheme day by day, and I think they're crazy. Anyway, the guy here, he's done a D against SSCT, SCTA. So what that's going to do is it's going to take that address and it's going to take you into a raw memory browse of that address. So it's going from the structure format into your raw memory form. Okay, you can continue that way. If you instead use the M action, so it's the same field again, SSCT, SCTA, which is the next pointer, just like the SSCT. What this is going to do now is it's going to go to that address and it's going to inherit the current structure and display the next guy in that structure format. So as you can see, you can just keep on pressing M beside that next field and you can just go through your entire structure and try a linked list in the structure to inherit the map. This is what a map structure looks like. So this again, I'm using the SSCT. It's one of my favorite little control blocks. It's nice and compact. And everyone recognizes it. So this is what a map statement would look like. Oh, sorry. Sorry about that. So here's the name of the map. We have a ref name, which is basically just documentation to say what the mapping macro is, and the length of the entire structure. And then you get these map-end statements nominating the field name, how long they are, the data type, and the offset from the start of the structure. It gets more interesting when you get down to things like the type of bit. The type of bit refers back to the type of byte and gives the hexadecimal value. So this is how we correlate bit settings inside of flag bytes. Going further on down through, you can see where the type of ADDR is instead of type char or type byte. That indicates to the code in SDSF that this is an address, so you can then use your D or G action against. Run chain is the next thing. So same sort of thing. I'm again in the SSCT, my general purpose go-to control block. And instead of typing an M against the row, I'm going to type RC to request a run chain. So obviously we're going to run a linked list, so we need some information first. So we need to know the offset to the next pointer inside that control block. So the SSCT, the offset is 4. SSCT, SCTA is the field. We need to know how long the next pointer is, if it's 4 or 8 bytes, or is it a 24 or 31-bit address, or is it a 64-bit address? And then we sort of say, well, how many bytes do you want me to show of this element within your linked list? We set the hexadecimal value. And then there's a traversal limit. So, how long should we go through this linked list before we stop? In case you've got a very long linked list or a circular buffer, and we're going to sit there chewing up CPU and storage for the next 10 minutes. Okay, so the default is 255, but you can obviously override that. And then you press enter. And what you get is a panel similar to what you're seeing now on the right-hand side, where you get a sequence of these blocks from the linked list. You've got the sequence number, as much hexadecimal content as you show in the contents field here with its EBCDIC, and there'll be the ASCII off the right-hand side as well. And then every single sequence within the linked list. And you, of course, can then select individual lines in this list, individual rows, and you can use D and G and M in exactly the same way. So it's just a way of providing you with a nice summary of your linked list and take actions. Okay, any questions on the mem command before I continue?
There is another question. Someone wrote, this looks very useful. Are most of the control blocks known to IPCS CBF also supported by SDSF memory mapping out of the box?
Out of the box. We don't have everything. We do have, I can't remember how many. It might be 50 or 60 core MVS ones. If you start using this and you think, oh, I'd really like that control block, please let us know. and we will add them. Or you can even knock one up yourself. You can if you're feeling courageous, you can add the definition. But normally, I would say, yeah, if there's something we've not got in the product, please let us know. It's not difficult for us to generate these new definitions, but we didn't want to oversupply with 2,000 mappings and then no one use it. So yeah, please let me know.
Thank you for that.
Yeah. All right, so sort of allied with this is a very simple screen we also have, which is a virtual storage map panel. So we can show you the start and end addresses of various storage boundaries. And if you are an unfortunate Roxa calendar customer, then we will dynamically insert rows for Roxa as well inside this screen. But you can see here the memory addresses. And we use this to sort of work out, well, when we're showing addresses in various other panels, where that address resides within the virtual storage. You can see that the other panels where we have the locations there. Address-based diagnostics is a new panel. I think it came in 2.5. It has a primary command of AD, which is the inverse of DA. And it's intended to show an address space centric panel, but nothing to do with how much CPU or IO you're doing, but purely just identification information and important control blocks. So it's intended that you would have to use it if you wanted to do any sort of memory problem investigations. You could use AD, and that's a point and shoot access to lots of handy spots, and then you can jump up from there. And you can also do actions against the row to look at common storage, private storage, and 64-bit memory objects. So it's your go-to guy if you're going to do memory analysis. And it looks something like this. Excuse the small text, but I wanted to sort of give you a full view of the sort of control blocks that we show. So it looks a little bit, if you look at the left-hand side of the screen, it looks a little bit like it does for DA, but then there's no stats about what it's doing. It's just a sequence now of control block addresses. You've got the ASCB, ASSB, ASXB, plus TCB, got the OUCB, and the JSAB if it's running under JES. Okay? And what you can do here, if you press point and shoot on any of these fields, it will inherit the ASID and the sysname from the row. Okay, so we'll go directly into theoretically a cross-memory browse session on that address space. We also include the CVT and eCVT addresses on every row as well, because you might well want to stay inside that address space, but you need to start at CVT or you need to start at eCVT and do a couple of jumps first before you're actually in the private storage of the address space that you're interested in. So that's why we have the CVT and the eCVT on each row. Okay, so common storage analysis. What can SDSF show you about common storage? So we started shipping the CSR panel back in 2.3 because it was quite useful to know as a systems programmer who was authoring all of your common storage. But all you saw was this summary panel. So if you look at the top screen here with all the lines in blue, that's like a summary. That's all you knew, that this job used up all this common storage. These numbers, this percentage, this data, whatever, but it gave you no details about what it's actually authored. With 2.5, we've added the JCS action, standing for Job Common Storage. You see a lot of the SDSF actions that to do with address spaces start with a J. And that normally means there's something after the J that says it's related to a job. So JCS shows you the Job Common Storage. So what this is going to do, it's going to drill down and show you each individual block of common storage that was authored by that job. And so it'll go into a screen that looks like this. Okay? So every single individual block of common storage is shown, including its subpool and its key, the date and time where it was allocated and orphaned. You can then use the address field as point and shoot, or you can do an S there, and that is going to take you into memory browse of that memory, so you can have a look at the content. And you can even have a look at the underlying control blocks. There's the GQE control block and the CAUB control block that FBS knows about. That keeps track of the common storage. You can even do a point and shoot on that and take a look at those blocks as well. But if you do have some address spaces that are leaking common storage, it's a very good way of finding out exactly what they're leaking, as long, of course, as you can recognize the eye catcher in the storage review. Another display we have is a new command, CS, which shows all of your common storage summarized by subpool and key. Okay? So you look in here, all your common storage subpools, with the subpool number, it's the fifth field, and then the key is the next field across, and we summarize it below the line, above the line storage. So you can have a look at all your common storage usage. However, you can now do an L action against the row. And what we're going to do now is that we're going to drill in to that common storage subpool and key combination and show you every single block of common storage for that specific subpool and key combination. You'll see on the title line that we've got the subpool number and the key up on the title line, and then we've got a load of lines there that show each block, whether it's allocated or free, and the owning, job name and job ID as well, and the ASID and the date. And then you can also look at the GQE as well. So that's all available from this detail screen for common storage. These are all the columns that we have off to the right-hand side. So we've got things like, fetch protection, whether or not the memory is fixed, the algorithm or the option used for key selection within that specific subpool. All those fields exist across to the right-hand side. Enough room, enough screen real estate to show everything in that original structure. We can also look at common storage by job name. So we looked at common storage by orphan common storage. We looked at common storage by subpool key. And now we're looking at common storage for an active job. So we have another command called AS, which is a little bit like DA, but this time it's focused on storage usage. And that's been available since ZOS 2.2. But in 2.5, we've added the JCS action, exactly the same action as we had on CSR. We've added that to AS, so you can zoom in to every single block of common storage owned by a specific address space. In this case, I've typed it beside the VTAM job name on this system. And then this takes you into a similar screen we looked at before, where you can see the addresses, you see the size, the subpool key, GQE, CAUB, all that sort of stuff. And again, you can browse that storage to take a look at it as you see fit. And this JCS action is on AD, it's on AS, it's on DA, and it's on the CSR panel as well. Okay, so it's in quite a few of the address space related. Any questions before I go on to private storage?
No additional questions.
Okay. All right, so you know where this is going, right? This is going to be very similar to common storage, but it's for private storage. So once again, we're going to start off on the AS command panel, and we're going to sort of say, right, I want to find out, things about my private storage. So we've got some interesting fields that you might not be aware of here. Okay, so when we first added AS, that was back in, I think, 2.2. There are some columns that weren't included because the functionality wasn't there in COS. But the good guys in Poughkeepsie added a control block called the LDAX, which enabled us as SDSF to get an idea of the private storage usage both above and below the line without having to go across memory into the address space. So it's a common storage resident control block that describes private storage usage within the address space from a bird's eye view level. So this means that we were able to add priv, priv%, epriv, and epriv% columns to the AS command. But because we care about compatibility, we had to add these columns to the end of the display, far right hand side of the screen. So some people don't realize that these columns exist. What I've done here, I've arranged them so that I bring them forward because I think they're quite interesting. So even on the AS screen here, you can immediately see the usage of private storage at summary level, the various jobs running in the system. We also have a new column called memobj real, which shows the actual real storage backing the memory objects for that address space. Because sometimes you have address spaces that are heroically defined within the program. I need 4 terabytes. And so you'll see the memory object is 4 terabytes, but then you only use 16K, inside your code, in which case you're only actually using 4 pages. Okay, so this is where the memobj real is quite handy because it'll actually show you, in use real storage backing that rather than enthusiastically defined memory object. And in SDSF 3.1, we added some interesting stats about elapsed time for the address space and also how your memory limit was derived, i.e., you've got this memory limit, where did it come from? Was it because you ran with originally 0M? Did it come from an SMS setting? Are you authorized? Was it specified in the JCL somehow? So you have this mem limit source column as well. If you do want to drill in to private storage for a single address space, the JM action stands for job memory, and that's been around since before my time. That was ZOS 1.12. And when you press the enter after issuing JM, you're going to get a summary of private storage usage by subpool and queue. And that's on a lot of other address space related panels as well. Go forward here. And it looks something like this. Okay? So you get a line of each subpool key combination, and we've gathered together all the statistics for that subpool key combination. But what we added in 2.5 now, very similar to common storage, is the concept of drilling down to show each block of private storage. So you type the L action beside the row. That's going to display a very similar panel to the common storage one, but this time it's geared around private storage. Once again, subpool key combination up in the title line. You can use the address field to browse the memory. But interesting on this screen, we actually show the owning TCB and the program name from the top RB. So you might be able to tell which program has actually allocated this storage. And this is in JES2's private storage, so has JES20 is not a surprise. So very similar to the common storage thing, but this time for private. And lastly, a little bit about 64-bit. Again, we're starting on the AS panel, but I could have started on AD as well. You can type in the JMO for job memory objects. That's been around since ZOS 2.4. So this is basically going to go into that address space and look at all of the memory objects owned by that address space. On this panel here, you'll see we have memobj real again, and we also have another column off to the right-hand side called memobj orcs. So it will show you the actual number of real frames backing the memory object and actually any auxiliary storage slots as well that are backing that memory object. So that's also quite handy to see again how much are we using that memory object. The JMO will take you here, where you're going to get a list of all the memory objects for that specific address space. I tend to use RMF when I'm doing this, because I know it owns both private storage memory objects and common storage memory objects. So you get the starting address, end address, its size and key, what guard pages it has, whether it's spectrum protected or not. And for common storage, we get some statistics about create date and program return addresses and stuff like that. I did ask the VSM guys why we don't get those stats for shared memory objects, and hopefully at some point in the future we might get that as well, because shared at the moment you don't get all. We also added on this panel as well in 3.1, I do believe. Again, statistics about real storage and auxiliary storage backing for specific memory objects. And we also now include the requester, home, and primary address space numbers at the time the memory object was created. That sometimes is handy when you're diagnosing problems. We've actually used that roughly with some problems we've had with DB2 disk, some memory objects in TCP/IP. So it's actually really quite a handy thing to have on the panel. Okay, so that comes to the end. So I'm allowing you now to go down the pub. If you're interested in more SDSF presentations, we do have a copy of most of the ones that we've given recently in the IBM GitHub, Education GitHub. There's the link there. You can cut and paste that, go and have a look, and there's all sorts of various things that we've given over the years. And please submit some session feedback to session code 9F. I'm very happy to take any questions from unmiked people now.
Perfect, yeah. So thank you, Rob, for taking us through that session, the advanced memory browse using SDSF. A really, really great session. Please, you guys will be able to unmute. So I'll do that right now. And you can ask any questions direct that you have. So I'll give it a few seconds and we can wait. I'll throw one first. Rob, you mentioned some of the people at Rocket will use the 3270 screen with the white background. Why is that?
Because they're crazy. I think some of them got vision problems, maybe. I don't know. There's one guy in particular.
Okay.
He used to drive me crazy. I couldn't do screen shares. I'd refuse. I think don't turn it black.
Yeah. Okay, then I guess no more questions. Then I'd like to thank everyone for attending the Large System Working Group stream and its third and final session for today. The next session is tomorrow at 9, and we have Steve Warren from IBM on what's new in ZOS 3.1. And a reminder, like Rob mentioned, please, if you can provide feedback, you can go to the Build Your Own Agenda or using the QR code on the screen right now. Thank you, everyone. And thank you, Rob.
Cheers, guys. Thank you.